Hi everyone, in this video I'm going to discuss limits and continuity for multivariable functions, functions of many variables. We're going to define limits of both sequences and functions in Rn. We're going to define what continuity means for functions of many variables, and we're going to work out some examples. Okay, so what is a function of several variables or many variables? These are the basic objects in multivariable calculus. We just mean functions which take in real inputs, or a vector in Rn, and output a vector in Rm. If m equals 1, meaning the range or the target space is one-dimensional, we say that f is scalar valued. While if m is greater than 1, we say that it's vector valued. If n equals 1, meaning the domain is one-dimensional, then we say that f is a function of a single variable. While if n is greater than 1, we say that f depends on several variables. Sometimes the domain of f will not be all of Rn, but will be some subset, which we can denote by u or some other letter. For functions of many variables, we can't visualize the graph of f like we can in the case n equals 1, m equals 1. But we can still define the graph to be the following set. It's a set in Rn plus m, the dimension of the domain plus the dimension of the range. And it's just a set of pairs x comma f of x, just like it is in the case n equals 1, m equals 1. Okay? So we first list the point in the domain, and then we list where that input goes to, its output. Okay? So we still can visualize this in a vague sense. If we imagine that this xy plane here represents Rn, and this sort of ellipsoid here, u, represents the domain of f, and then the z-axis represents Rm. So this is kind of a cartoon, it's not reality, except in the case n equals 2, m equals 1. We can still imagine that the graph of f is some kind of surface that comes out and is above this domain u, and its height represents the element of Rm, where x, so the point x here would get mapped to somewhere on the surface here, f of x, where f of x is represented on this Rm axis. Even though this cartoon doesn't really represent reality, it's still helpful to think in terms of graphs sometimes and to use our intuition in low dimension. Okay, before we can talk about limits and continuity of functions of many variables, we need to discuss some topology. So I need to tell you about open and closed sets. And we begin by talking about what an open ball is. So if we're given a point x in Rn and a positive constant r bigger than 0, the open ball centered at x with radius r is just a set of all points in Rn which are less than r away from x. So we can visualize it. We have some x. We draw the circle of radius r centered at x. And then the ball is just all the points that are strictly inside, not including the actual circle itself. So it's all the points that are strictly inside. Okay? A subset U of Rn is called open if every point of U is the center of a ball contained entirely within U. So let's imagine that this shape here is my set U. I'm thinking of U as being the points inside, but not including the boundary. Then any point inside, no matter how close to the edge, I can always find some ball centered at that point that stays entirely inside. If I'm very close to the edge, of course, the ball has to be very small, but it's nevertheless true that every point inside of this yellow curve, I can find a ball that stays inside of the yellow curve. So that's what we mean by open set. Of course, if the set U did contain the yellow curve itself as part of it, then I could find a point here on top of the curve so that any ball that I opened would contain some points that are inside and some points that are outside. And so these points would not satisfy the definition of being open. And so if U contained this yellow curve as part of its set, then it would not be open, because these points that are kind of on the boundary here would not be in the interior of U. Okay, so this brings us to the notion of boundary points. Okay, so we say that a point X in Rn is a boundary point of a set U if for every R, if we look at the ball centered at X of radius R, then it intersects U non-trivially. So this is the notation for the empty set. Empty set. So I'm saying that the ball centered at X of radius R does intersect U. So there's some points that are going to be inside. But also, it's not the whole ball. So the ball is not entirely inside of U, because if the ball is entirely inside of U, then this intersection would be the entire ball. And I'm saying it's not. So there are some points that are outside. So this is what it means to be a boundary point. We see that this point here is a boundary point, because any ball we open will have some points inside of U and some points outside of U. Okay, so when we speak of the boundary of U, we just mean the set of boundary points of U. And we denote it like this partial symbol next to U. This partial U is the set of boundary points of U. Okay? And finally, we say that a set U is closed if the boundary belongs to U. So if the boundary is a subset of U. In other words, every boundary point of U belongs to U. So in the case of this set, I would need the entire boundary to belong to U, and then U would be closed. It would not be, of course, open. And in order to be open, I need that the entire boundary not belong to U. So you can see that a set cannot be open and closed at the same time, except in some very special situations, like the set of all points in Rn is both open and closed, and the empty set is both open and closed. But apart from that, you can't be open and closed, but you can be neither. So imagine that I had included only part of the boundary here inside the set U. Then these points would not satisfy the definition of openness here, because these points here on the edge would belong to U, but would be such that I can't open a ball at those points and stay entirely inside of U. On the other hand, these points over here that I neglected to include would include some boundary points which are not in U. So it would be neither open nor closed. So open and closed is not exactly a dichotomy, although sometimes for many sets it's close to a dichotomy. Okay, let's see some examples of open and closed sets. So first of all, open balls are open. Let's see a proof of this. So let's recall that the definition of the open ball was this. The ball centered at X of radius R is the set of all Y in Rn such that the Euclidean distance of Y to X is less than R. Okay, so let's check that this is open. In order to check that it's open, I need to know that every point belonging to this ball has the property that I can find another ball centered at that point which belongs entirely to the ball. So let's prove it. Let's select our favorite point Y in BR of X, and the ball centered at X of radius R. Okay, what does this mean? This means that the distance from X to Y is less than R. Okay, so again, remember here that this notation represents the Euclidean length of this vector. Okay, well, let's call this number, whatever it is, since it's less than R, let's give it a name. Let's call it S. Okay, so S is the distance from X to Y. Let's draw a picture. Okay, so here's the ball. The point X here is maybe in the middle. The point Y is near the edge. And this distance here is S. And the distance here is r. Okay, so I need to now open a ball centered at y that still stays entirely inside. So I would like to open some other ball like this. Okay, so in order to do so, I just need to specify the radius. So what radius can I pick here that's small enough that this blue ball here would still be entirely inside of the big yellow ball? Well, we can see that by the triangle inequality, I should choose r minus s, which is still a positive number. Okay, so we claim that the ball of radius r minus s centered at y is entirely inside of the ball of radius r centered at x. If we could prove that, then we would be done, because we will, for an arbitrary point y, have found another ball of that radius, r minus s, that's entirely within our set. Okay, so let's check this. Now, this picture here that we drew, where we convinced ourselves that this could be r minus s, this picture was really true by the triangle inequality, right? Because if we have any point in this blue ball here, the distance from x to that point can be bounded by r by simply first going to y and then going to that point, and then knowing that by the triangle inequality, the distance from x to this point is less than r. So this is just by the triangle inequality. Okay, so now in order to prove that, of course, that one set is inside of another, I need to take an arbitrary point in the first set and show it belongs to the second set. So I'm going to say by the triangle inequality, if z belongs to the first set, the smaller ball centered at y, then, well, what do I want to check? I want to check that the distance from x to z is less than r. And I can see that by the that I'm sort of set up to use the triangle inequality. So I just use the triangle inequality like this. The distance from x to z is less than the distance from x to y plus the distance from y to z. And now I see that actually I have equality here. So I have, this is equal to s plus r minus s, which equals r. Now, I didn't quite write these inequalities correctly, because I should actually, this is not an equality, this is a strict inequality. There we go. So I needed to get this to be strictly less than r, so I was worried for a second. But this one equals s, and this one, y minus z, is less than r minus s, because that's what it means to be in the open ball. So that's the end of the proof, because we showed that x minus r, or x minus z, is less than r. That means that z belongs to the bigger ball. That's true for any z that belongs to the smaller ball, which means that we have proved this subset relationship, which means that we've checked that the original set is open. We're next going to move along to discussing limits of sequences in Rn. I'm going to assume that most of you are familiar with limits of sequences in R1, that is, limits of sequences of just real numbers. So let's give ourselves a sequence xk, which is a sequence in Rn. Okay, so now we have to be careful here, because xk does not denote the coordinates of one point in Rn. It denotes a sequence of points in Rn. So we imagine that we have x1, x2, maybe x3 over here, maybe x4 over here, x5, and so on. And each of these points lives in, 2, maybe 3-dimensional space. Okay, so each of these points has in coordinates. All right, so we say that the limit as k goes to infinity of xk equals x, where x is some other point of Rn, if the limit as k goes to infinity of the distance from xk to x is 0. Okay, so when you first look at this, you might find this a bit unsatisfying. Did I not just define what it means to have a limit in terms of what it means to have a limit? Okay, yes, but here, this equal sign here that I'm defining, the orange equal sign, is defining a limit of elements of Rn. And over here, this number here, xk minus x, Euclidean distance, the Euclidean distance of xk minus x. This does involve vectors in Rn, but strictly speaking, this thing is just a number. It's a number that depends on k, so it's a sequence of just real numbers. And I'm assuming that you know what it means to take a limit of a sequence of real numbers. So if you know what it means to take the limit of a sequence of real numbers, then you know what this means, even though there are vectors in Rn inside. And so I can use this to define the limit of elements in Rn. Okay, so if this makes you happy, then you can just take this as your definition. But there's another definition that I want to explain, which is equivalent, which says that for every real number epsilon positive, there exists a capital N depending on epsilon, so N epsilon, such that once you're beyond the point in the sequence indexed by N epsilon, after that, all the terms in the sequence are in the epsilon ball centered at x, or in the closure of it, in the closed ball. So, in other words, if you give me a tolerance epsilon, I can find a point in the sequence such that after that point, the entire sequence is within the tolerance of the desired limit. And this is what it means to have a limit. If I can do this for every epsilon. Okay, so there's, and this is actually how we defined limits of real numbers back in single variable calculus. So the equivalence here can be related to the equivalence between limits and the epsilon in definition here. Okay. So sometimes when you're doing actually exercises, you'll be able to reduce a limit of elements of Rn, and you'll be able to just directly bound the Euclidean distance between xk to x in terms of something that's obviously going to 0. And you'll be able to conclude this in a simple way. But other times you may want to revert to this epsilon in definition. All right, let's discuss limits of functions. So let's say that we have an open set U of Rn. And we have a function whose domain is U and which maps into Rm. So again, the domain is n-dimensional, the range is m-dimensional. We give ourselves a point x0 in U in the domain, and we give ourselves some other vector in Rm in the target space. Okay? Then we say that the limit as x goes to x0 of f of x equals z0. So I'm going to define now what's in this orange box. Now what this means is that every sequence I take of points in U converging to x0, where I'm not allowed to take x0 itself. So this notation U backslash this point here means the set of all points in U, but excluding x0. Okay, so you imagine that U is some domain. I have some point x0, and then I have a sequence of points that are getting closer and closer and closer to x0. Okay, but they can't ever be x0 itself. Okay, so if I have a sequence of points converging to x0, then the sequence of outputs must also converge to z0, where this limit is in Rn and this limit is in Rm. Okay, so again, if you go back to this picture and you have a point x0 here, and you have a sequence of points converging to it, and over here you have the range, this is Rm, and here you have f of x0, or sorry, you have z naught, and you have the sequence of outputs of f. These are the sequence of points that the sequence over here got mapped to. Then I want that sequence to converge to z naught. Of course, there's an equivalent way to state this in terms of epsilons and r's, just like there was for the limits of sequences in terms of an epsilon in definition. Okay, so the equivalent way to state that the limit of f as x goes to x naught is z naught is to say that for every epsilon positive, I can find a radius r, so that if the input belongs to the ball centered at x naught of radius r, and isn't the center point itself actually, then the output f of y will land in the ball centered at z naught of radius epsilon. So in other words, if you have z naught here, and you have a ball of radius epsilon, and epsilon's the tolerance, and you want to land in that ball, and over here I have a point x naught, then I can find a ball of radius delta here, so that if I take any point inside this ball, not including x0, and I map it over through f, I'm going to land in this epsilon ball centered at z naught. This formalizes the notion that as the inputs converge, the outputs converge. Okay, let's discuss some properties of limits. First of all, limits may not exist. This may not be a surprise to you because this was also the case for functions only of one variable, just functions from r to r. So just because I've defined a function doesn't mean that I can just take a limit. Okay, the second property I want to speak of is that limits are unique provided they exist. Now let me explain why. Now, this is kind of easy, but if you haven't seen it, it's good to see it. So what does it mean to be unique? It means, well, if I go back to the definition of limit back here, I wrote this down and said that the limit of x goes to x naught of f of x equals z naught if some stuff happens. But this, strictly speaking, I shouldn't have been able to do this because I don't know that there's only one limit. And maybe there's two z naughts which satisfy this definition. And by writing this notation here, I'm kind of implicitly saying that there's only one such limit. Of course, I'm using this notation because limits are unique, but we have to prove that. So let's suppose that we have 2 points, z1 and z2, which are possible limits. Okay, so suppose that I have, according to my definition, and limit x goes to x naught of f of x equals z2. Okay, now what I want to show is that z1 equals z2, but I'm not allowed to just string the equal signs and say, well, this is equal to this, therefore z1 is equal to z2, because that's kind of assuming what I want to prove. So I have to actually check the definition. Okay, so what I'm going to do is I'm going to look at the distance between z1 and z2. Okay, and I'm going to apply the triangle inequality. Okay, so I'm going to say that this is less than, and I'm not going to write this, but I'm going to assume I have some sequence xn converging to x. Actually, maybe I will write it. So let's just assume that, let's take a sequence xn converging to x0. Okay, so then I can have z1 minus z2 is less than f of xk minus z1 plus f of xk minus z2. This is again by the triangle inequality, the second or third time we've used it so far. Okay, and the point is that if both of these are limits, then both of these have to converge to 0 as k goes to infinity. Okay, so I have that z1 minus z2 in Euclidean length is less than 0. So this implies that they're equal. Okay, and that's what we mean by limits are unique. We mean that if you take two limits for the same sequence, then they have to be equal. Okay, and this is true at the level of, I wrote this proof as though I was taking the limit of a function, but this is true just at the level of limits of sequences, of course. So the function f here was kind of beside the point. Okay, let's talk about why limits are linear. Okay, so what I mean by linear is these two properties, that if I take the limit of a sum, I get the sum of the limits, and if I take the limit of a scalar multiple of the whole sequence, then I get the scalar multiple of the limit. Okay, so this is again the triangle inequality. Let's see why. I'm not going to write a full formal proof. I'm just going to kind of sketch it for you here. So I'm going to take xn minus plus yn minus x plus y, because I'm going to call this limit, I'm going to call x, and this limit I'm going to call y, just for shorthand. Okay, and so what I'd like to do is I'd like to look at the difference between the term in the sequence xn plus yn and the sum of the limits. Okay, and this is by the triangle inequality, less than xn minus x plus yn minus y. And each of these goes to 0 as n goes to infinity. I guess I shouldn't really be using n, because n is usually the dimension of my space, not the index of the sequence, but that's okay. This goes to 0. Okay, and that is because x is the limit of xn, so the first one goes to 0, and yn is the limit of yn, so the second one goes to 0. So the triangle inequality just gives me that limits are linear. The proof of the second property is almost exactly the same. Okay, so now that we know about limits, let's discuss the property of being continuous. Okay, so we are given an open set U in Rn. We're given a function on U, which is valued in Rm. And we're given a point inside of the domain U called x0. And I want to define what it means for f to be continuous at x0. Okay, this just means that the limit as x goes to x0 of f of x exists, and it equals f of x0. That's all that it means. So far, when I defined a limit of a function, I didn't relate the limit as x goes to x0 to anything whatsoever about f of x0. Just f of x0 had nothing to do with the limit of f of x as x goes to x0. And that's the reason that we insisted that when we take sequences, we have to exclude the point x0. We're not allowed to take points in the sequence to be equal to x0, and so forth. But now, when I define continuity, I do relate them. I say this thing over here, which had nothing whatsoever to do with f of x0, actually has to equal f of x0. And if that's true, then f is a continuous function. Okay, or it's continuous at x0. We say that it's continuous if it's continuous at every point in its domain. Sometimes we'll say f is continuous in U if it's continuous at some points and not others. Or if it's continuous at every point of a subset of U, then we'll say it's continuous in that subset. Of course, because the notion of continuity involves limits, and limits can be expressed in terms of epsilon delta definitions or epsilon r we were using before, I can express the notion of continuity in the same way. Okay, and this is a very useful way to think about continuity. It sort of helps you understand what continuity means when you state this definition, although when students first see it, they're sometimes a little intimidated by it. So let's talk our way through it. F is continuous at a point x naught if, for every epsilon positive, there's a delta positive. Earlier I was calling this r, now I call it delta, such that if you look at all points which belong to the ball centered at x naught of radius delta and belong to the domain, then the output of those points must be in the epsilon ball centered at f of x naught. So if you want to land near the output, f of x naught, of the special point x naught, where near is defined any way you like by any epsilon, then there's a way to do it. There's a way to pick a delta so that if you start near enough to the input, you will land in this ball centered at the output. Let's try to draw a cartoon about this so that we can see this better. So the way to think about the epsilon is that epsilon is the desired tolerance. Now this number epsilon, somebody comes and tells you, okay, so you think f is continuous. Well, why don't you try it for epsilon equals 10 to the minus 6. So it could be 10 to the minus 6. And as long as your adversary specifies epsilon and gives you one particular epsilon, 10 to the minus 6 or 10 to the minus 9, once they fix epsilon, then you have the chance to find a delta. And your job is to find a delta so that any input value, which is delta away from the special number x0, will land inside of this box here. It'll land inside this sort of red zone. So you're hoping that the graph of f looks something like this. And maybe it comes down here, maybe it comes up. But before it gets inside of this interval, it stays inside the red zone, and it doesn't leave it until after it's outside that interval delta. Okay? If your adversary picked a smaller epsilon, maybe half as big, then you would have to pick a much smaller delta in order to keep the curve inside of the desired tolerance. So this is how you think of it. Your adversary picks a tolerance. You've got to find a threshold delta so that if the input level is within the threshold, the output, f of those inputs, will be within the desired tolerance of f of x naught. Okay, let's talk about properties of continuous functions. Now, because continuity was defined in terms of limits, and we had sort of similar properties for limits, these properties, well, I guess the first property anyway, is not too surprising. Okay, so linear combinations of continuous functions are continuous. This is quote unquote obvious. Now, if you're a student who's never seen this before, you'll want to check it for yourself. But I claim that this is not so hard from the fact that limits have obey linearity. So it's obvious from the linearity of limits. Okay, so for example, I'll go ahead and explain f of x naught plus g of x naught. This is what f plus g evaluated at x naught is. This is just the limit of f of x as x goes to x naught plus the limit as x goes to x naught of g of x. Here I use the fact that f and g are continuous. So if f and g are continuous, I can replace f of x naught with this limit. I can also replace g of x naught with this limit. Okay, and now I use linearity of limits. Limit as x goes to x naught of f of x plus g of x. Okay, and that's actually what we wanted to prove because this is what f plus g of x is. And of course, this one up here is what f plus g of x naught is. So you see that this proof involved almost nothing. I just used the assumption that f and g would be continuous, the linearity of limits, and the definition of what it means to add two functions, and it pops out. Okay. Okay. So let's discuss the fact that products of continuous functions are continuous. Well, this is also just inherited from limits. I didn't actually discuss this property, but it stems from the fact that if I have two sequences xk and yk, and I guess when I speak of products, I'm really assuming that m equals 1 or I'm taking the dot product or something, because if they're valued in Rm, then I can't really speak of products without being more specific. So let's just speak of m equals 1. So this is again inherited from limits of sequences of real numbers. So let me see. So if I have that the limit of xk is x, and that the limit of yk is y, then I can look at the limit of xk, yk, and know that this is the limit of xk times the limit of yk, meaning x times y. Okay, so from this property, in a proof just like the one I did above for the linearity, I can get that the products of continuous functions are continuous. Okay, let's go over this last one, which is also easy. The composition of continuous functions are continuous. So let me talk about this one. Okay, so why is this true? Let's suppose that f is g composed with h, meaning that f of x is g of h of x. Okay, and I'm going to assume that everything is set up so that this composition makes sense. So if h goes from Rn to Rk, g goes from Rk to Rm, then f would go from Rn to Rm. So we assume that the dimensions line up so the composition makes sense. Okay, then I want to look at the limit as x goes to x naught of f of x. This is the limit as x goes to x naught of g of h of x. Okay, now I'm going to use the fact that g is continuous, and I'm going to say that I'm going to use the fact that both are continuous. So I'm going to notice that this thing goes to h of x naught. Okay, so if I had any sequence xk, then h of xk would go to h of x naught. But that would then mean that the whole thing, since g is continuous, goes to g of h of x naught. Okay, so this thing has to be equal to g of h of x naught, which is, of course, f of x naught. Okay, so f is continuous. So if that was a little too quick, I encourage you to pause the video and think about it for 5 minutes and try to write your own proof. Okay, finally, let's see a couple of examples all worked out. So let's look at the first one. So we're asked to take the limit of a sequence in R2. We have x times y divided by x squared plus y squared. Now when I see a problem like this, very, very often you're going to have xy going to 0, 0. And you're going to have the numerator and denominator both blowing up along the way. Otherwise, it becomes kind of easy. So what I'd like to do is I'd like to think about along sequences of points x and y going to the origin, how big can I make this fraction and how small can I make it? So I can kind of doodle on the side here and try to imagine what's going on. So in multiple dimensions, you can approach the origin in different directions. That's what's different between limits in R2 and limits in R1. So here's the origin. And I could imagine taking different paths to get there. I can take sequences that go like this. I can take sequences that go like this, or go like this, or go like this, or spiral in, or whatever. Okay? And it needs to be that every sequence finds the same limit. Okay, well then you can see what's going on here, because if I take the point x equals y, so I kind of come in on this 45-degree angle from the x-axis here. If I approach along x equals y, then what do I get? I get that x times y divided by x squared plus y squared. If x is equal to y, then the numerator is x squared and the denominator is 2x squared, then this is 1/2. Okay, so if I approach along this direction here, exactly on the line x equals y, or down here, just anywhere I'm on this line, then what I get is 1/2. And you can see now that it's possible to get something else. What happens if I approach along the direction x equals 0? So I approach on the y-axis, or actually on the x-axis. Then the numerator is 0. So if I approach along x equals 0, then I see that xy divided by x squared plus y squared equals 0. So these two do not agree. So by the uniqueness of limits, or even by the definition of limits, the limit does not exist. The limit does not exist. Okay. All right, let's talk about the second one. If I add +1 to the denominator, does anything change? Well, you can see that actually a lot changes, because now the denominator can't go to 0 while the numerator goes to 0. So the numerator is going to 0 for sure. And the denominator is always bigger than 1. So this is clearly going to go to 0. So we think that the limit should be 0. Okay, because the numerator is going to 0 while the denominator stays bounded below by 1. To prove this, though, we have to come up with some kind of argument. Okay, so there's various ways that you can do it. Observe that the absolute value of xy divided by x squared plus y squared plus 1 is less than absolute value of x times absolute value of y. Because if I make the denominator equal to 1, if I just throw these terms out, I'm going to get bigger, because I'm going to make the denominator smaller. I'm going to get bigger in absolute value anyway, because I'm going to make the denominator smaller. Okay, well, x times y, each of those is less than the square root of x squared plus y squared. Okay, because if I threw this part out, I would get absolute value of x back. And if I threw this part out, I'd get absolute value of y back. So I just made it bigger. And this is the length of the vector xy squared. And this function clearly goes to 0. Okay, it goes to 0 because the square function is clearly continuous. And this is a continuous function of the distance. So as the distance goes to 0, so must this a continuous function of the distance. So the square of the distance you're allowed to know goes to 0 as the point goes to 0. Okay, so that's it for this lecture. Next time we will introduce the concept of differentiation of functions of many variables.